This is sort of a pre-lecture. It's coming right before our lecture on sampling distributions and central limit theorem, so we'll learn what those are. Actually, this very video here is going to show you what a sampling distribution is. So first of all, what have I got here? I've got just a normal distribution, and let's just say that these are kaiju. Gotta make up something. Kaiju. These are the weights of individual kaiju. So according to this data on the side here, the mean weight of a kaiju is 16 tons. Now if you read the scale here, that's a 0, that's a 32. Right in the middle here is 16 tons. So yeah, that's where the peak number of kaiju. Most kaiju have a weight of 16 tons, and then there's a whole bunch that have weights close to 16, and then there's not as many that have weights that are way out here. By the way, let's say these are all adult kaiju, just to be safe. So anyway, individual kaiju have weights with a mean of 16, and it says here a standard deviation of 5. So that's what this red thing is showing, by the way. So the mean of 16 is here, and then it goes up plus or minus 5, just to kind of show you what it means to go up plus or minus 1 standard deviation. You might remember something about the inflection point. If this is a bell curve, it's kind of concave up here. It's like the bowl is up, but then it turns right around here to concave down, which is like a bowl facing down. And then over here is another inflection point where it changes back to a bowl that's face up. So that's how you define standard deviation. That's how you define the width of this curve. You might remember that 95% rule, that if you go plus or minus 2 standard deviations, you expect to find 95% of your kaiju weights. So let's do that. If the standard deviation is 5, then 2 standard deviations is 10. So at 16, go up and down by 10, which means 6 to 26. So if we read here, 0, 1, 2, 3, 4, 5, 6 is about here. And 32, 31, 30, 29, 28, 26 is about here. So yeah, between 6 and 26, you do get most of your data, like 95% of your data is within 2 standard deviations of the mean here. So this is a really nice bell curve we got going here. So if that's all we were interested in, is the mean weights of individual kaiju, notice I keep using that word individual kaiju, this is how the weights of individual adult kaiju are distributed. Again, mean of 16, standard deviation 5, cool. Now we're going to do something different. What we're going to do is we're going to sample, and it says here n equals 5. We're going to take a sample of 5 of these kaiju chosen completely at random. We're going to take a sample. Watch, here we go. Boom. I said boom. Okay, boom. So see what has happened. We took a kaiju that had a weight of this much. Another kaiju had a weight of this much. I mean, where are we? We're at, I don't know, 11 or something here. And then there's what, like 13 or something. Then we had 2 kaiju that had a weight of somewhere around the mean of 16. And then he said, okay, that's our sample of 5. Now take the mean for that sample. So if you take the mean of these 5 particular kaiju, the mean turns out to be this. And so that blue box is placed here. Do it again. Boom. Take another sample of 5. Looks like we were a little bit high, a lot a bit higher that time. Let's take another sample of 5. So again, we've grabbed 5 kaiju at random from the individuals, and then we took that sample of 5 and took its mean weight, and its mean weight came out, I forget which blue box it was. One of those blue boxes, right? So you can keep doing this over and over and over. Boom. And now the question I have for you is, what do you think the distribution is going to look like here? What's the blue distribution going to look like? Now this, by the way, is called a sampling distribution because it's a distribution of sample means. It says here distribution of means when the sample size is 5. So if you take 5 at a time and measure their means, you're going to get some kind of a distribution down here too. What do you expect it to look like? Now I'll give you a hint. It will be another bell curve, but it'll be different in some way, right? How do you think the bell curve will be different? Well, one way you might get at it is to say, notice every time we take 5, right, we typically get 5 that they're not all way up here, and they're not all way down here. We usually get some, maybe some from up here, some from down there, more from in the middle, and so on. And so when you take the mean of these, that brings you back towards the middle, right? And so these blue things tend to be in the middle. They always tend to be in the middle. And if you want to end the suspense, I can watch this. I can do 100,000 samples. Boom. In fact, if I do that 9 more times, 1, 2, 3, 4, 5, 6, 7, 8, 9. There, we've done over 1 million samples now. We got a bell curve. We sure got a bell curve. I can fit a normal right there. Boink. There, see? Bell curve. But it's skinnier. It's narrower. It's got a smaller standard deviation. We used to have a standard deviation of 5. Now we got a standard deviation of 2.24. Much smaller, actually. Notice the mean here is 16, which is the same as the mean here, 16. So if all the kaiju, if the individual kaiju have a mean of 16 tons for a weight, then if you sample 5 at a time, and you know, any one sample is not going to guarantee to have a mean of 16 at all. Most will, but you'll have some that are close and some that are a little farther away. But notice you don't have a whole lot that are way far away, right? So you end up with a smaller standard deviation for this mean. Cool, right? Now, let me ask you this question. We were sampling 5 at a time. What if we were to sample 16 at a time? What do you think will be the effect? I love the animation, so let's do that again a couple times. So we're sampling 16 kaiju, individual kaiju. This is our sample of 16 individual kaiju. Now we take the mean of that 16, the mean for that group, and the mean for that group is right in the middle here. Do it again. Take 16. Ooh, we got one way out here. He's an outlier, man. So we got an outlier kaiju. Came out the same. How do you like that? Let's try that again. 16 kaiju, and the group of 16 has a mean that's about this much. Let's end the suspense, do 100,000 of them. Bam! Bam, 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 bam. And so you get a much skinnier normal distribution. Notice the mean of these samples is still 16. The mean is going to be the same, but the standard deviation is a lot less. We had a standard deviation of 5. When you sample 16 at a time, those groups of 16, their mean weight will have a standard deviation of only 1.25. Okay, so that's the part you need to see, is that when you sample a whole bunch at a time, you get smaller and smaller standard deviations. I'm just going to do one more, 25 at a time. Let's just do it. Boom, 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 boom. Now the standard deviation is only 1, right? So the bigger your sample size, the mean of your samples will come out the same as the mean of the parent population, the individuals. But the distribution, the standard distribution, deviation, the standard deviation of your sample means will be a lot less than the standard deviation of the individuals. Or another way, a standard deviation for the mean of 25 at a time is a lot less than the standard deviation for the mean of an individual. Something like that. Okay. So it's a lot of words to kind of digest, but I think the visual, that's the main thing. The standard deviation is getting skinny. Okay, so with that, we can go to our lecture and explain what this is going to mean to us. And I have to find the off button.